We're going to take a look now at rational exponents, which we've actually looked at very briefly before. Before we can do much of anything, though, with rational exponents, we need to take a look at some higher powers. Set the calculator up to show us some of these higher powers. In the y1 column, I've put x cubed in, and in the y2 column, I've put in x to the fourth. To be able to simplify some of these higher rational exponents, of course, which means higher roots, we need to understand these higher powers. We know what our perfect squares are. You know, for example, 1 squared is 1, 2 squared is 4, 3 squared is 9. You really need to be able to recognize some of your perfect roots, third roots and fourth roots. For example, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216. You also need to be able to recognize your perfect fourth powers for the purpose of taking fourth roots. 1 to the fourth is 1. 2 to the fourth is 16. 3 to the fourth is 81. 4 to the fourth is 256. 5 to the fourth is 625. 6 to the fourth is 1296. And frankly, if you go much beyond that, it's not really practical to expect that you'd be able to remember these, but it is good for simplification purposes to be able to spot them. Now, if we need to be able to evaluate, not simplify, but evaluate, and of course when you're told to evaluate, that means you can plug it into the calculator. For example, if they said evaluate the third root of 27, and we should already know what it is because here it is on our list, but as far as just punching it into the calculator, here's the easiest thing to do. It's best to remember that when we were looking at square roots, like square root of x, put a little index of 2 there, we learned that that's the same thing as x to the 1/2. Therefore, we can assume safely that the cube root of x can also be written as x to the 1/3. The fourth root of x can be written as x to the 1/4, and so on. Fifth root of x could be written as x to the 1/5, etc. Of course, if you ask where's the 1 coming from, well, we assume that this x has got a 1 on it. We can take advantage of this with our calculator. For example, we just said find the cube root of 27 and evaluate it. Well, I can put in the 27, hit that caret key, which means to any power, in parentheses put a 1/3, and easily come up with a 3. Let's evaluate the fourth root of 81, which of course is 81 to the 1/4 power. On the calculator, this is easy to do. 81 to the power 1/4, and that's 3 as well. So we see that 3, when you raise it to various powers, gets higher and higher values. Now, one interesting thing about your third root versus your fourth root. Your fourth root, since it's the opposite of an even power, will not give you a real answer if you put a negative underneath here. But the third root will. For example, if you're looking for the third root of a negative 125, you may immediately think, well, you can't do that because it's a negative number. With the square root, you can't. With the fourth root, you can't. But with the third root, you actually can. I will take the negative 125 to the power. Again, for third root, we'll do the 1/3 power, and you get a negative 5 coming out. So that is, not only is it a real number, it's a nice rational real number. So this is what we do for evaluate. Again, remember, that's what we've been doing here, evaluate. That just means go to your computer, your calculator, and punch it in. Now, as far as simplification is concerned, it's a different process. If I ask you to simplify third root of 40, if you were to go to the calculator put in a 40 to the power 1/3, we would get a very ugly answer, an irrational answer as a matter of fact. This is not the kind of thing we want to see. Alright, so for simplification, here's what we have to do. We have to figure out how to take the 40, break it apart, so that that'll give us something we can take the cube root of. If you go to your list, perfect cubes, we see that 8 is a perfect cube, and 40 can be broken into 8 times 5. Cube root of 8, which is 2. The cube root of 5 you can't take. This is reminiscent of what we did with our perfect squares, only this time it's with perfect cubes. And on occasion, perfect fourth powers. Let's take the cube root of a 3,000 and see if we can find how to simplify that. Again, not punching it into the calculator and evaluating, but simplifying. Now let's see, 3,000, and it's a cube root. Don't see anything right off the top of my head that comes out of it, so we might have to do this one the hard way. We're going to take that 3,000 and start breaking it apart. Take 3 times 1,000. 3 times 10 times 100. 3 times 10 times 10 times 10. Now, the perfect square, if it was a square root, I would say, well, here's 2 of a kind, there's my perfect square. Since it's a cube root, I say here's 3 of a kind. So I'll break this up into 3 times 1,000, and apparently 1,000, if I was to go down this list far enough, I'd be willing to bet that I would discover that 1,000 is in fact a perfect cube after all. And I just didn't spot it, but that's okay. We broke it apart and we found it. So this is a 1,000 times 3. Cube root of 1,000 is 10. Cube root of 3 is what you leave behind. And the same procedure is going to work just fine for your fourth roots. If we take the fourth root of 32, we could go look at our list of perfect fourth powers, and we're going to need to go back up this list a bit because we're working with a much smaller number than what we're seeing here. Let's see, do we have anything here that goes into 32? There it is, 16. Alright, so we're going to break this apart into the fourth root of a 16 times 2. And as we can see, the fourth root of 16 is 2. So this becomes a 2 times the fourth root of 2. And that's your simplification process with constants. Now the next thing we need to do is learn how the variables simplify. And lucky for us, that's actually easier. We need to learn how to write in exponential form anything that's given to us in a radical form. And we have a rule that says the nth root of x to the m power is x to the m over n. That helps us because that gets it into a fractional form, and we can simplify fractions. So let's take a look at how this works. Let's say we had the fourth root of x to the third. And again, our only goal right now is to get it into the exponential form. Let's see how this is going to work. Let's see, it's going to be an x for the base. The power is 3. The root is 4. So it's a 3/4 power. Pretty easy. Let's try another one. Third root of y to the 8th. Y is the base. 8th power on top. Third root on the bottom. There we go. That's easy. Now let's see how this helps us simplify. Now under simplify, let's see what we can do with this. If I had the third root of w to the 21st power, I could rewrite this as w to the 21/3, 21/3, which reduces to 7, and I'm simplified. If I had a, fourth root of a, to the 60th power, I could rewrite it as a to the 60 over 4, which simplifies to a to the 15th. Very easy. Some rational expressions where you do not end up with a nice integer power, therefore you can turn them back into a radical. For example, if I had the 4th root of x squared, I could rewrite that as x to the 2/4 power, 2/4, which reduces to 1/2. So we can turn this back into a radical, because 1/2 power means square root of x. If I had the 9th root of z to the 3rd, I could write this as a z to the 3/9, which reduces to z to the 1/3, which can be rewritten back in a radical as the 3rd root of z. If I had the 8th root of n to the 6th, I can rewrite that as n to the 6/8, reduces to 3/4 power, which is the 4th root of n to the 3rd. Again, notice the 3 on top is the power, the 4 on the bottom goes back in as the root. So just being able to simplify fractions makes it easy for us to simplify some of these radicals, and we can also simplify some constants using this similar technique. Let's say we had an 8 to the 4/3. Now we can do this on our calculator. I can just say 8 to the power 4 over 3. The calculator will give us a nice answer. But where did that answer come from? Remember, we got a 16. Let's see what that is. 3 on bottom means 3rd root. 4 on top means 4th power. I'm choosing to do the power last so I can work with the smallest number possible. 3rd root of 8 is 2. And 2 to the 4th, there's where that 16 came from. Let's try another one. Let's take a 64 to the 2/3 power. Again, the 3 on the bottom is the root, and the 2 outside is the power. 3rd root of 64, we know, is a 4, and 4 squared, there's a 16 again. So it's easy once these once these constants are written in the proper form to evaluate them. And we can even take, like, back in radical form, we can take like the 5th root of 3 to the 15th power, rewrite this as 3 to the 15/5, which becomes a 3 to the 3rd. Easy to work with. Once we understand the connection between the radical and the exponential form, it's easy to work with. As a matter of fact, we can go back to working with variables in just as easy a fashion. If I had the 4th root of x times the 4th root of x cubed, I could rewrite them both. This is an x to the 1/4 times an x to the 3/4. Again, when we multiply like bases, we just add the powers. 1/4 and 3/4 is 4/4, so we get an x to the 1st. That's pretty easy. If I had the 4th root of z to the 3rd and bring that to the 4th power, this is going to be a z to the 3/4 to the 4th again. And when you raise something to a power more than once, you multiply. So I'll just take 3/4 times 4. That's a 3. So z to the 3rd. Let's try one more example working with a variable. Let's take the 3rd root of x to the 6th and square it. Again, relying on the fractional powers, this is an x to the 6/3 squared, which is an x squared squared, which comes out as x to the 4th. Alright, easy enough? Good.